When you're learning math, you have the basic number crunching, right? Solving for a variable. And I give you, like we had for homework, I give you systems of equations, you do the number crunching, and then you solve it. But really, the ultimate goal is that you can think through a problem. God made us with brains that can adjust to situations and figure out how to solve problems. And so what this section does is it takes different types of word problems that create systems of equations. And then you're going to set up those equations and solve them by either substitution or elimination, either way. All right, and so the first type of problem that it gives us is talking about two different numbers. So for most of your word problems to this point, you've really been able to say I have one variable and I'm going to set up an equation for this one variable and then I'm going to solve for this one variable, right? But when you have problems like this, you actually end up with two variables. And the only way to solve two variable equations is to either have one to plug in or to have two different equations using the same variables so that you can do a manipulation like substitution or elimination to get rid of one. All right, and so this is talking about two different numbers. Two numbers, the sum, that's key, is 23 and the difference is 81. We do not know either one of the numbers, so we are going to say, well, I have an X and I have a Y. Those are my two numbers. Sum, what does that mean? Addition. So the sum that's equals 23. And then they tell me the difference. So same two numbers, but now I am subtracting, and that is negative 81. As you can see, this is a systems of equations. And then you are free to solve whichever method, other than I would not graph this guy, right? But any method, you can either solve by substitution, get one of those variables alone, plug it in, or you can solve by elimination. Personally, if I see that I already have a variable that's a positive and a negative of its coefficient, I'm going to use elimination here. So I personally would solve by elimination here, which means I would just add down, since it's already set up for me. These are going to cancel. And then I have x plus x gives me 2x. Don't forget your equal sign. 23 and negative 81 is negative 58. And then my final step to solve for x is to divide by 2. X equals negative 29. It told me to find two numbers, so I am not done. I need to go to one of these equations and plug in my negative 29. So I'm going to say negative 29 plus y equals 23. If I add that 29 to both sides, I will get that y equals 52. So my two numbers are negative 29 and positive 52. Mr. Perry has invested a total of $10,000 in two stocks. AmeriCorps returned 8%, while BankCorp returned 10%. How much did he invest in each stock if his total return was $850? All right, so he has two stocks. We do not know either one of those. So we do not know either one of the stocks. We're going to assign variables to the two stocks. So I'm going to say he has stock X and stock Y. All right, now, what we do know is that the amount of stock X plus the amount of stock Y that he invested is going to total that $10,000. All right. Now, if I set up X, that I'm going to say is the AmeriCorps. And if I set up Y, I'm going to say that is the Bank Corps. All right. So I do want to kind of note that over to the side when it's something like this and not just two numbers, because the next line is about to tell me specific things about those. What is my percent return on my AmeriCorps stock? 8%. How do I write that, by the way? 0.08, right? So if I take the 8% times how much I invested, that's how much my return is for the AmeriCorps. What's my percentage that he earned on the Bank Corps? So 0.10 times Y will give me his return for the Bank Corps. And then the total that he was returned last year was $850. That's how much he earned on that stock that he invested, okay? $850. Now, here's the thing about this type of problem. I'm going to get rid of my decimals, me personally, for the most part. There are times when you can leave them in because you're using a calculator, so it really doesn't matter anyway. But if I'm solving by substitution or elimination, I like to get rid of my decimals. So I'm going to use my little decimal trick here where I just move it over the total number of decimal places that I have. My highest number of decimal places is 2. So I'm going to move everything over 2 decimal places down here. And remember, if I move that in decimal place, I do need to fill it in with zeros, right? Because that decimal was the end of the 850. Now, you don't have to do that. I personally always do that. I just get rid of my decimals, all right? So then I have 8, 10, and 85,000, okay? Now, I personally would also solve this by elimination, but you can solve by substitution. If I look, I have something rather simple. This Y would be easy to get rid of. I can multiply this entire top equation by -10, multiply the X by -10, multiply the Y by -10, multiply the 10,000 by -10. All right. So that's personally how I would solve this. I prefer elimination method. If you prefer substitution, in fact, the example that I'm about to give you for you to work on, substitution and leaving your decimals in may be easier just because the decimals are so big. But if it's something like this where you can quickly get rid of the decimals and you have something like a 10, multiplying by 10 is really easy. All right. And so that's my preferred method here is elimination. If you do it by elimination, then you're going to see that you have your Y's cancel out. -10 and +8 gives me a -2. And -10,000 and positive 85,000 or 185 give me a -15,000 because I did add that 0. And then I'm just going to divide by 2. That is divisible by 2. Divide both sides by that negative. We get X equals 7,500. What did that tell me? Well, that told me how much stock he put in AmeriCorps. So I'm going to say 7,500 was in AmeriCorps. Well, if he invested a total of 10,000, I can go back to my original problem. It was X plus Y equals 10,000. If he invested a total of 10,000 and 7,500 was in AmeriCorps, how am I going to solve for what was left? Yeah, just plug it in. So we're just going to plug in my 7,500 and subtract it over, right? Subtract it over, you're going to get Y equals 2,500, which means that he had 2,500 invested in Bank Corps. So this is what your answer would look like here. You need to tell me which one is which, because this does matter. It does not matter, by the way, how you set your variables up. You could have said that X was Bank Corps and Y was AmeriCorps, but the 8% had to go with the AmeriCorps, the 10% had to go with the Bank Corps. When you see these, you're going to see like one line that kind of gives you one of the equations, and then you're going to see something else that gives you more information. That's going to be kind of usually your second equation. And then you're going to have to set them up and decide what's the easiest way to solve these. So if you do it elimination, I would probably recommend getting rid of my decimals, because you don't have to. You could multiply everything by negative 0.07 if you'd wanted to and just have decimals there. But this way I didn't get rid of my decimals. I just did substitution. So I subtracted my y to get x equals 150,000 minus y. I plugged that in for my x, so 0.07 times that group, distributed, combined my like terms, subtracted the 10.5 over, divided by the 0.0075, and I got again that y equals 80,000. So either way, whether you solve by elimination or substitution doesn't matter. So I would look at this one and I would say they're 412 miles apart, which means you're going to add their distances. And so I would just set up my initial chart for my first bus. We'll say bus A and bus B. All right, the rate times the time equals the distance, right? I don't know the rate of my first bus, but I know the other bus is traveling slower. Well, if it's slower, I'm going to subtract 3 miles an hour from it. They give me the time for both of them, 4 hours. And so technically they're doing substitution here with this x minus 3, that second rate. But for me, I would rather go ahead and set it up this way. Distance is going to be the 4 times the x. Distance here is going to be 4 times the x minus 3. And then since they are a certain number apart, 4x plus 4 times x minus 3 equals the total distance apart of 412. And so if I have something like this, I'm actually not going to do a systems of equations. I'm literally doing substitution, building in my initial equations, right? Whereas they do it a little bit different. They actually set up an equation for the rates and then plug those in. I would just do it this way. Distribute your 4. 4x plus 4x minus 12 is 412. You have 8x. Add your 12 over, so that equals 424. And x equals 53. This is which bus? Well, I set this up as bus A. So this guy is going 53 miles per hour. He is going 3 miles slower, so he's going 50 miles per hour. So that's one type of distance, rate, and time where you're technically doing a substitution for your rates. Rate 1 and rate 2, but we know rate 2 is rate 1 minus 3. And so instead of just setting up systems of equations here and doing substitution, I just set it up all within mine, right? The next distance, rate, and time, though, is really what you're going to see more when you have what you think of as a standard systems of equation. There's going to be two things. One is going to be boats that go with the current and boats that go against the current. And the other one is going to be airplanes that go with the wind and against the wind, okay? Think about what's helping and what's not helping. So if we look at this example 4, during rainy season on the Amazon, Pastor Sosa can travel 60 kilometers downstream in the same time that it takes to travel 30 kilometers upstream. If his boat can travel 16 kilometers an hour in still water, what is the average speed of the current on this stretch of the river during the rainy season? All right. So for these, I also set up a chart. And for this type of chart, I am going to have a downstream and an upstream, or if it's an airplane, you're going to have with the wind, against the wind, all right? You still have a rate, a time, and a distance, all right? That's how it works. So if I am going downstream, is my current helping me or hurting me? Is the current helping you or hurting you when you go downstream? It's helping you, right? It's pushing the boat with you. Upstream, you're actually working against it. All right. And so you have the rate of the boat, how fast the boat is going, and then you have the rate of the current, how fast the current is going. All right. When you're going downstream, you actually add these. If you add the boat and the current, that's going to be the total rate that you're traveling. All right. But if you're going upstream, you have to take how fast you're going and subtract the current. So my rate here for problems like this is going to be the motor in which you're traveling, that person, that device, whatever it is, whether it's the airplane or the boat. And then what is helping you, you're going to add. What's hurting you, you're going to subtract. All right? With airplanes, they'll say with the wind. That's like downstream. Against the wind, that's like upstream. Okay? Time. They actually don't tell us what the time is. What they do say, it says in the same time. So I know that this is actually the same variable here. All right? Now, going downstream, he can go 60 kilometers. That's actually the distance that he travels. And going upstream, he only goes 36 kilometers. That's the distance. So for this one, this is going to be a little bit different. This actually tells me how fast his boat travels, right? So this actually tells me that B. How fast his boat travel is actually 16 kilometers. So this is going to be that 16 kilometers plus the current. This is going to be the 16 kilometers minus the current. Does everybody see that? Yes? All right. So for this first one, I'm going to have my rate times my time. So my time, I don't know, but I know that it's t. Multiply. If I multiply by a group, I need to put parentheses. That should be equal to my distance. Well, I know my distance downstream is 60. All right. The next one, time. That's going to be the 16 minus the current. And that is going to equal 36. Now, here's the key. If I have something like this where I am going to distribute and get something that is a variable times a variable in there, all of a sudden substitution looks much prettier. All right. Because this guy is set up to isolate the t for both of them. All right? Isolate the t for both of them. This is what I mean. So for this first group here, this t times the 16 plus, right? I can actually divide both sides by that entire group. So I have this t 16 plus c equals 60. I can divide both sides by that 16 plus c. And for this, t equals 60 divided by 16 plus c. All right? For this second one, t 16 minus c. I can divide both sides by that group. And my t will equal 36 over 16 minus c. In this case, I'm using substitution. All right, if I distribute that t, it's going to be a variable times a variable, and it gets to be a real pain. All right, and so now I have both things equal to t, which means I can set them equal to each other. All right, so I can say 60 over 16 plus c equals 36 over 16 minus c. This should look familiar. This should look like a ratio. When we solved for ratios way back in Algebra 1, you had something over something equals something over something. What's the method to solve a ratio? What's the method? Yeah, it's cross multiplication, all right? So I can literally just cross multiply here, okay? This is the easiest way to do this one, I promise. So if I take this, I can cross multiply him. All right, so I'm going to take this and I'm going to cross multiply, and I'm going to say 60 times the group across from it equals 36 times the group across from it. And this is the easiest method to solve this one. Now, there are going to be some distance, rate, and times where they give you the time, right? And they give you the distance. And then you have something that you can solve by another method of substitution or elimination. But if they give you something like this where isolating the variable gives you this division, you may want to set it up with this, all right? So then when I distribute, I'm going to get that, all right? Now, here's the thing. You can set it up with your two variables if you want to, but sometimes that's going to get very, very confusing. All right. Solving this, you're going to get your variables to one side, your numbers to the other. So I'm going to add my variables over here. I'm going to pull my numbers over here. My current is 4 kilometers per hour. If you do it with the other way, which is how the book does it, you have to think of it like a literal equation, meaning you have to cancel out your variable with a coefficient that is also a variable. And it gets a little confusing. Not that this wasn't, but it gets a little confusing with that one.